There was a time before planets, before moons, before oceans or mountains or life. A time when the space that would one day become our solar system was nothing more than a vast cloud of drifting particles. This cloud was silent. It held no form. It spun slowly in endless darkness. Yet inside this stillness, a great transformation was waiting to begin. Every grain of dust carried the memory of stars long gone. Every swirling particle held the seeds of worlds that did not yet exist. The future of our solar system rested inside these ancient fragments. The cloud stretched across a wide region of space. It was made of fine dust and gas left behind by older dying stars. This material floated weightlessly through the void. Nothing within it pointed toward order. Nothing suggested structure or stability. Everything existed in a dreamlike state of drifting suspension. Yet nature has a way of turning chaos into shape. And this is where the story of asteroids begins. For they are the first solid witnesses of creation. They preserve the earliest secrets that planets later lost. As the cloud slowly moved, gravity began its work. It drew particles inward. It gathered dust into streams. It pulled everything toward a center that did not yet shine. This center would one day ignite and become the sun. But for now, it was only a growing knot of material gathering strength. Around it, the cloud thickened. Motion increased. Heat rose. The stillness slowly shifted toward energy. Inside these regions of growing density, dust grains brushed against one another. They clung together. They formed tiny clusters. These clusters attracted more grains. Over long ages, they became pebbles. Pebbles merged into larger bodies. These early bodies drifted through the swirling cloud and collided again and again. Some shattered. Some merged. But many survived. These survivors became the first solid stones of the young solar system. They were small but ancient. They were rough but stable. They were the ancestors of all asteroids. Asteroids are not random stones scattered through the void. They're the oldest preserved chapters of the solar origin story. They formed before any planet existed. They hardened before Earth cooled. They were witnesses while the sun was still young and faint. Their surfaces carry records of early heat and early collisions. Their minerals hold the fingerprints of ancient cosmic chemistry. Each asteroid is a time capsule from the beginning. To understand the birth secrets of the solar system, we must first understand these humble stones. For planets grew large and changed. Oceans formed and erased early marks. Volcanoes rose and destroyed old layers. Tectonic plates recycled ancient ground. But asteroids kept their memory. They hold the story intact. And through them we can look back billions of years and see the moment when everything we know was just beginning to take shape. It follows the slow awakening of the solar cloud. It traces the path of dust as it transforms into stone. And it reveals how these first stones became the storytellers of creation. The early cloud began as a frozen, quiet place. Yet hidden within it were forces waiting to unfold. Gravity was one of these forces. Heat was another. Motion was a third. These forces worked together in silence, shaping the future piece by piece. No sound was made. No light was present. Everything happened in slow, deliberate motions across vast stretches of time. But these motions were enough to bend the cloud into a new form. The center of the cloud grew heavier. It drew more and more material inward. As this happened, the cloud flattened into a spinning disk. This disk glowed faintly from internal friction, though it still remained mostly dark. Within this disk, temperature varied. Some areas remained cold. Others warmed. The warm inner regions shaped different minerals than the cold outer regions. And these minerals would one day determine the types of asteroids that formed. In the warmer inner area, rocky minerals condensed. Metals hardened. Silicates formed. These materials built the foundation of stony and metallic asteroids. In the cooler outer region, ices remained solid. Water ice, carbon ice, methane ice. These materials formed the ancestors of comets and icy bodies. Thus, even before planets formed, a pattern of diversity existed. The solar system was already separating into zones that would later define everything from asteroid composition to planet structure. The earliest stones drifting within the disk moved in circular paths around the center. Some paths crossed, some stones collided gently, others hit with intense force. Every impact changed their shape and size. Through these endless interactions, the first generation of asteroids took form. They were small bodies, yet they represented the first stable pieces of the emerging solar architecture. These stones were not smooth. They were irregular, filled with fractures, marked by ancient heat. Their surfaces captured the signatures of the earliest events. These signatures remain visible today on many meteorites that fall to Earth. Scientists study these fragments to understand what the solar system looked like before planets matured. They uncover minerals that formed under conditions no longer present on any planet. They find tiny inclusions that are older than Earth itself. These materials are the most ancient objects humans have ever touched. The silent birth of asteroids continued for millions of years. The disk kept spinning. The center grew hotter. The surrounding material thickened. The future sun approached ignition. But the first solid stones drifted steadily through this changing environment. They were witnesses to every stage. They carried the memories forward. As we move deeper into the story, these early stones will reveal more secrets. They will show how collisions shaped the system, how heat altered minerals, how water arrived, and how planets began to grow. They will guide us through the earliest ages of cosmic history. The young solar system continued its slow transformation. The center of the spinning disk grew hotter and brighter as more material fell inward. Pressure increased. Heat rose to levels never seen before in this region of space. Then, in a moment that reshaped everything, the central mass ignited. Nuclear fire awakened. Light burst outward. The sun was born. This birth was not gentle. Waves of scorching radiation swept through the disk. Solar winds pushed dust outward. Heat reshaped minerals. The calm, drifting world of early stones changed into a realm of intense energy. Yet this energy did not erase the stones. Instead, it altered them. It forged new minerals inside them. It left marks that would survive for billions of years. These marks are part of the ancient story that asteroids still carry today. As the sun grew brighter, the inner regions of the disk heated dramatically. Rocky minerals melted, then cooled again. Metals separated from silicates. Dense metallic droplets formed inside molten stones. When the droplets cooled, they became solid beads of bright metal. These beads later became part of many metallic asteroids. Science now identifies these features inside meteorites as relics of ancient heat. They reveal that the earliest stones lived through intense cycles of melting and cooling that shaped their internal structure. The outer region of the disk was still cold. Here the sun could not melt ice. Frozen water and frozen carbon remained solid. As the sun awakened, the outer stones evolved differently. They remained mixed with ice and dust. They formed softer bodies. These icy stones would one day become the ancestors of comets and distant small worlds. Their history preserved the cold secrets of early space, while inner asteroids preserved the fiery secrets. The radiation of the young sun did more than heat the stones. It pushed lighter particles outward. This gentle pressure moved fine dust away from the inner region and into the broader disk. This movement changed the distribution of minerals and shaped where different types of asteroids would later form. Heavy metallic grains stayed closer to the sun's silicate-rich stones, formed a wide band beyond them. Icy stones gathered far away. These zones formed the blueprint of the asteroid belt and the outer small body regions we see today. Inside, the inner region collisions became more frequent. As solar heat stirred the disk, stones moved faster. Their paths twisted. They struck one another with increasing energy. Some bodies shattered and their fragments scattered across the disk. Other bodies grew larger as they absorbed smaller stones. These growing bodies became the first building blocks of planets. They are known as planetesimals. Yet not all early stones joined this growth. Many remained small. These small survivors became asteroids. Why did some stones grow large while others stayed tiny? The answer lies in location and timing. Stones near regions of high density merged quickly and became planetesimals. Stones in quieter zones remained small and drifted unharmed. The asteroid belt formed in one of these quieter zones. It existed between two powerful regions of the disk. On one side, the pull of the young sun and inner planetesimals drew material inward. On the other side, the growing power of the giant planet Jupiter pulled material outward. These two forces balanced and blocked the formation of a single planet in the region. As a result, large growth never completed. Countless small bodies remained trapped. They became the asteroids. While the sun grew stronger, the stones captured its effects. Some stones heated internally due to radioactive decay. Early short-lived radioactive elements produced heat within their cores. This internal heat melted some asteroids. The molten material separated into layers. Heavy metals sank inward. Lighter silicates rose upward. These layered asteroids became small versions of planets. Their interiors changed forever while their exteriors remained ancient and unchanged. Some of these differentiated asteroids later broke apart due to collisions. Their fragments scattered across space. When these fragments fall to Earth, they reveal cross-sections of ancient worlds that no longer exist. Other asteroids remained cool. These bodies stayed untouched by internal melting. Their minerals stayed primitive. They preserved the earliest dust grains that formed in the solar nebula. These stones are like untouched chapters from the first pages of cosmic history. They contain particles older than the sun. Tiny grains within them formed near ancient stars that lived and died long before our solar system even began. When scientists examine these grains, they uncover stories that reach beyond our solar birth back into the wider history of the galaxy. The sun continued to brighten. Solar winds strengthened. They blew away the remaining gas of the disk. As the gas thinned, the stones moved more freely. Collisions continued, shaping their surfaces. Some asteroids remained smooth. Others became fractured. Many gained crater marks that survive to this day. Every crater is a memory of an ancient impact. Every fracture records a moment of cosmic change. As the gas cleared, planets began to appear. Their orbits stabilized. The inner region gave rise to rocky planets, while the outer region produced giants of gas and ice. Through all these changes, asteroids remained. They were small, yet enduring. They held the memory of every stage. They had seen darkness before the sun. They had felt the first radiation. They had lived through melting and freezing. They had drifted while planets grew around them. And still they waited to tell their story. The young solar system was no peaceful place. It was a realm of constant motion where stones drifted on paths shaped by gravity, heat, and chaos. Every object moved at great speed. Every orbit crossed another. Every journey carried the possibility of impact. Collisions filled this ancient world. Some were gentle, some were violent. All of them shaped the birth story of the solar system. Asteroids formed within this realm. They did not grow in silence. They grew in a storm of impacts that sculpted their surfaces and changed their internal structure. Each impact left behind a signature that would last for billions of years. These signatures survive today in the meteorites that fall to Earth. Scientists study these marks to reconstruct the nature of early collisions. Through these marks, the stones speak. In the early era, collisions were frequent because the disk was dense. Countless stones drifted through narrow paths around the young sun. The slightest gravitational shift changed their motion. When two stones approached one another, gravity pulled them closer. They collided. Sometimes they stuck together. Other times they shattered into fragments. These fragments drifted away and formed new stones. This constant cycle of creation and destruction shaped every asteroid that exists today. Large impacts produced heat. When stones struck with great force, their surfaces melted. Molten droplets sprayed outward. Some droplets cooled into tiny beads that became embedded inside nearby stones. These beads are visible today in the most ancient meteorites. They reveal the temperatures and pressures that existed in the early collision era. Their structure tells scientists how long they melted, how quickly they cooled, and how intense the early impacts were. Not all collisions were catastrophic. Many impacts were slow and gentle. In these cases, stones pressed together and fused. This gentle merging built larger bodies one layer at a time. These bodies became early planetesimals. Some planetesimals continued merging until they grew into full planets. Others stopped growing and remained small. These small survivors are the asteroids. Their modest size is not a sign of weakness, but a sign of survival. They remain stable in a world of giants. The asteroid belt became a special region of collisions. Because Jupiter was forming nearby, its gravity disturbed the paths of stones in this region. These disturbances prevented the stones from merging into a planet. Instead, they remained separated. Their orbits shifted constantly. They collided again and again. This is why the asteroid belt contains so many bodies of different sizes and shapes. It is a laboratory of collisions frozen in time. The stones within the belt felt the pull of Jupiter throughout their existence. Jupiter tugged them outward. The sun pulled them inward. These opposing forces created gaps in the belt known as resonance zones. In these zones, stones could not survive. Their orbits became unstable. Objects entering these regions were either thrown out or smashed into other stones. These chaotic movements preserved the belt as a scattered population rather than a single planet. Some collisions were large enough to break entire asteroids into fragments. These fragments drifted into space, forming asteroid families. Each family shares a common origin. Their composition carries the mineral signature of the original parent body. Scientists identify these families by tracing the paths of their orbits backward through time. When the paths converge, they reveal the moment of destruction. These reconstructions allow scientists to map the ancient history of events that occurred billions of years before humans existed. Inside, some asteroids' collisions created fractures that extended deep into their interiors. Over time, fine dust filled these cracks. Later impacts compacted the dust into new layers. These layered structures show the repeated cycles of destruction and rebuilding that shaped the earliest stones. No planet carries such detailed layers of ancient events. Only asteroids preserve them. Some asteroids became rubble piles. These bodies are made of fragments held loosely together by gravity. They formed when a large asteroid broke apart and its fragments drifted together again. These rubble piles have empty spaces inside them. They are fragile, yet stable in space. When spacecraft visit them, instruments can sometimes detect hollows inside. These hollows represent ancient voids created by violent destruction and slow rebuilding. The collision era also delivered vital materials across the early solar system. Water ice from the outer region traveled inward. It struck rocky bodies and delivered water to their surfaces. Carbon-rich stones moved inward, as well carrying organic molecules. These deliveries seeded the inner planets with the building blocks of oceans, and perhaps even life. Without collisions, the inner worlds would have remained dry and barren. Asteroids witnessed all of this. Their surfaces contain the marks of water. Their minerals contain traces of ancient carbon. These traces show that collisions were not only destructive, they were creative. They mixed materials from different regions. They blended the solar system into a unified whole. As the collision era continued, some larger bodies formed molten cores. Their interiors separated into layers of metal and rock. But even these bodies were not safe. A single giant impact could break them apart and scatter their layers across the solar system. When pieces of these differentiated bodies fall to Earth, scientists find metallic cores mixed with rocky crusts. These fragments reveal the internal structure of ancient worlds that no longer exist. The story of collisions is essential to understanding the birth secrets of the solar system. Collisions shaped every asteroid. They determined what minerals formed, what layers developed, and what fragments survived. Without collisions, the solar system would not look the way it does today. It shows the contrast between destruction and creation. It reveals how impacts built planets and preserved stones. It explains how the asteroid belt became a monument to ancient turbulence. And it prepares us for the next stage of the story, when heat, internal processes, and chemical transformations will deepen the mystery even further. The early solar system was shaped not only by collisions and sunlight, but also by secret fires that burned deep inside the first stones. These fires were invisible from the outside, yet they transformed many asteroids from simple fragments of dust into complex bodies with layered interiors. These hidden fires came from radioactive heat, a quiet and powerful force that influenced the fate of every early stone. Short-lived radioactive elements existed within the ancient dust that formed the stones. These elements released heat as they decayed. This heat melted the interiors of some asteroids, even though their surfaces remained cool. Inside these bodies, metal separated from rock and sank toward the center, forming metallic cores. Above the core, lighter minerals rose, forming rocky layers. These asteroids became tiny versions of planets. They never grew large enough to become worlds, yet they carried internal structures similar to planets like Earth. These molten interiors created new minerals that did not exist in the outer dust. As the molten material cooled, crystals formed. These crystals captured the chemical conditions of their time. When modern scientists examine meteorites, they find these crystals preserved in perfect detail. Through them, they can measure the temperature, the pressure, and the chemical environment that existed inside the asteroid billions of years ago. This makes asteroids a living record of the hidden fires that shaped the young solar system. Not every asteroid experienced this transformation. Many remained cold and untouched. These bodies preserve the earliest minerals that condensed directly from the solar nebula. These minerals are called primitive grains. They formed in the first moments when dust cooled around the newborn sun. They contain details from the very beginning of the solar story. Some of these grains are even older than the sun itself. They originated in ancient stars that exploded long before the solar system was born. When scientists hold these grains, they hold fragments of ancient stellar worlds. The difference between melted asteroids and untouched ones reveals the diversity of heat in the early system. Some stones accumulated enough radioactive material to melt. Others did not. Size played a role. Larger stones retained heat, while smaller stones cooled quickly. The timing of formation also mattered. Stones that formed early contained more radioactive energy than stones that formed later. Thus, the history of each asteroid is shaped by its birth moment, its size, and the materials trapped within it. Inside the melted asteroid's molten rock sometimes rose through fractures and formed new crusts. When impact struck these bodies, they broke open the crust and released molten material that cooled rapidly. These rapid cooling events produced special textures inside meteorites. These textures reveal how fast the molten rock cooled and how deep it was buried. Through these signs, scientists reconstruct the inner geography of long-vanished worlds. Some asteroids developed metallic cores similar to the core of Earth. When these bodies later broke apart, fragments of their metallic cores drifted through space. If such fragments reach Earth, they appear as shiny metallic meteorites. These meteorites are among the most ancient metals humans have ever seen. Their composition shows that metals separated from rocky minerals billions of years before Earth even finished forming. They reveal that planetary-style processes began on asteroids long before planets existed. Other asteroids stored water within their minerals. This water was not stored as liquid, but as tiny molecules trapped inside crystals. When these crystals break apart, they release the ancient water. Some meteorites contain enough water to show that early asteroids once underwent chemical reactions between water and rock. These reactions created clays and other hydrated minerals. They also produced organic molecules that are important for the chemistry of life. The water in these stones did not originate on the asteroids themselves. It came from icy particles that drifted inward from the colder regions of the disk. When these icy grains collided with warmer stones, the ice melted and reacted with minerals. This mixture of heat and water created chemical diversity inside the asteroids. These chemical signatures remain preserved today. Through them, scientists can trace the path of water across the early solar system. As chemical reactions continued, some asteroids produced organic compounds. These compounds formed when carbon-rich dust mixed with water and minerals. Over millions of years, complex molecules emerged. Some of these molecules resemble the building blocks of life, though they are not alive themselves. They show that organic chemistry was already active long before Earth formed oceans. It suggests that the seeds of life may have been scattered through the inner solar system by asteroids. Inside other asteroids, heat caused minerals to recrystallize. These new crystals grew slowly in the dark interiors of ancient stones. Their patterns reveal the duration of heating and the depth at which they formed. When meteorites containing these crystals fall to Earth, scientists can measure their age with remarkable precision. These ages act like clocks inside the stones. They show when the asteroid melted, when it cooled, and when it experienced later impacts. Some asteroids remained solid on the outside, but molten on the inside. Their surfaces stayed ancient while their cores transformed. This means that the outer layers of these bodies preserve the earliest history, while their inner layers reveal later heating events. When impacts later shattered these bodies, fragments mixed together. Some fragments came from old outer layers. Others came from younger inner layers. These mixed fragments now fall to Earth and provide a layered story within a single stone. The hidden fires inside asteroids also shaped their shapes and densities. Some bodies became dense and metallic. Others became porous and filled with empty spaces. Some developed smooth interiors with thin crusts. Others became cracked by repeated heating and cooling cycles. These differences still exist today. They allow scientists to identify which asteroids underwent melting and which remained cold and primitive. Through all these internal changes, asteroids preserve the earliest chemical history of the solar system. They stored minerals that formed in hot inner regions. They carried water and organic material from cold outer regions. They blended these ingredients through heating, cooling, and collision. Their interiors reveal how the solar system mixed its materials long before planets took shape. The hidden fires did not last forever. As radioactive elements decayed, their heat faded. The interiors cooled. Solid layers formed again. The molten cores froze. The outer crust hardened. The asteroids entered a long period of quiet. Yet the signs of their fiery past remained. These signs survived every later collision and every journey through space. They remain visible today in the meteorites that reach Earth. The story of hidden fires shows that asteroids are more than simple rocks. They are ancient laboratories where the first chemical experiments of the solar system took place. They reveal how heat, water, and minerals interacted in the earliest ages. They show how materials mixed across the solar system. They provide clues to the origins of organic chemistry and possibly even the ingredients of life. The solar system was young, yet already filled with complexity. Light from the sun spread across the disk and touched every stone, every grain, and every drifting fragment. This light did not only warm the stones. It changed them. It triggered reactions. It altered minerals. It reshaped molecules. Through these effects, sunlight became a silent sculptor of asteroid chemistry. The stones that formed under this light still carry its signature today. When the sun first ignited, its light contained intense radiation. This radiation moved outward in waves and struck the dust-filled disk. Dust grains absorbed this light and heated rapidly. Some grains melted. Others reacted with surrounding gas to form new minerals. These early reactions produced a family of minerals called high-temperature condensates. These minerals are found inside many primitive meteorites. They reveal that sunlight shaped the earliest grains long before the stones grew into larger bodies. Another form of light-driven chemistry occurred on the surfaces of icy grains. In the colder regions of the disk, sunlight broke apart molecules trapped in the ice. These broken fragments reacted with one another and created new compounds. Some of these compounds contain carbon, nitrogen, and hydrogen. These are the same elements important for organic chemistry. When the icy grains drifted inward and mixed with rocky dust, the organics they carried became part of the young asteroids. As the early sun grew brighter, its ultraviolet light began to affect the stones in the middle regions of the disk. This ultraviolet light altered carbon-rich dust. It caused thin organic coatings to form on the surfaces of the grains. These coatings helped the grains stick together. This increased the rate at which small grains merged into larger clumps. Thus, sunlight played a role in the first stages of stone formation. Inside, growing planetesimals sunlight could not reach. Yet the chemical signatures formed at the surface remained trapped as the stones grew. These signatures act like markers. They show which grains formed near the sun and which formed farther away. When scientists analyze meteorites, they can identify these markers. Through them, they map the ancient light environment of the early solar system. In some regions, sunlight triggered reactions between silicate minerals and gas. These reactions created new compounds that condensed onto the surfaces of grains. Over time, these layers thickened. When the grains merged into stones, the layers merged as well. These layered minerals survived every later stage of heating and every collision. They reveal the changing chemistry of the solar nebula as the sun continued to brighten. Another important chemical process occurred when sunlight interacted with water in icy grains. Sunlight broke apart water molecules into hydrogen and oxygen. Some of the oxygen reacted with metals, forming oxides. These oxides later became part of meteorites. They reveal how sunlight shaped the oxidation state of early minerals. Through these clues, scientists can determine how much ultraviolet light reached various regions of the disk. As larger asteroids formed, the sunlight continued to drive changes on their surfaces. Their exposed layers experienced cycles of heating and cooling. Heat altered their minerals. Cooling preserved the new structures. Over millions of years, these cycles created weathering patterns. The patterns remain visible in some meteorites today. They show how the stones aged in sunlight long before they became part of planets. The sunlight also pushed small grains outward. This gentle pressure shaped the chemical layout of the disk. Heavy grains stayed closer to the sun while lighter grains drifted outward. This separation influenced what materials ended up inside each asteroid. Some asteroids became rich in metal. Others became rich in silicate. Others gained organic material. These differences reveal the action of sunlight across the disk. Inside the asteroid belt, sunlight helped produce a wide range of chemical diversity. Some asteroids collected minerals formed in high heat. Others preserved cold, fragile compounds. This variety exists because the belt lies in a region where sunlight had both strong and weak zones. In some parts, the heat was intense. In others, the stones remained cool. This created a chemical map across the belt that scientists still study today. Sunlight also shaped the behavior of dust that settled onto asteroid surfaces. Fine grains accumulated in layers. When sunlight warmed these grains, they reacted with gases that still existed around the stones. Over time, thin chemical films formed on the surfaces. These films captured traces of the early solar atmosphere. When fragments of these asteroids fall to Earth, the films reveal the composition of the solar nebula. Some asteroids rotated rapidly due to past impacts. Their fast rotation exposed different parts of their surfaces to sunlight. This caused uneven heating. Uneven heating created fractures and stress patterns. These patterns allowed gases and water to escape or enter the minerals. Through this, sunlight created pathways for chemical exchange. These pathways changed the minerals inside the stones. In deeper regions of the disk, sunlight played a smaller role. Yet even there, its influence could be felt. The drifting of light particles pushed fine grains into distant zones. These grains carried with them minerals created near the sun. When they reached colder areas, they mixed with ice-rich stones. This mixing formed hybrid asteroids containing high-temperature minerals alongside frozen compounds. These unusual combinations are found in some meteorites. They reveal how sunlight transported materials across vast distances. Over millions of years, the early chemical landscape became more complex. Heat from radioactive decay worked inside the stones, while sunlight altered their surfaces. Collisions mixed warm and cold materials together. Through all these changes, asteroids preserved the results. Their minerals became a record of light, heat, and motion. Their chemistry became a reflection of the entire solar birth process. Inside some asteroids, sunlight-driven reactions created amino-like compounds. These compounds are not alive, yet they are essential for the chemistry that leads toward life. They show that the earliest steps of complex chemistry can occur naturally on small bodies in space. They also show that organic chemistry began far earlier than anyone once believed. When fragments of these asteroids reach Earth, scientists examine them under microscopes. They find traces of ancient organic coatings. They find grains altered by ultraviolet light. They find minerals shaped by high-temperature radiation. Each of these clues reveals part of the ancient chemical environment. Through them, scientists reconstruct the influence of ancient sunlight. The chemistry shaped by early light reveals something profound. The sun did not simply illuminate the solar system. It created it. Its light sparked reactions. Its radiation shaped minerals. Its pressure moved grains. Its energy built the foundations of planets. And through the asteroids, these effects remain preserved. The ancient fragments that wander through the vast, dark sea of space continue to serve as living witnesses of the early solar kingdom. Every asteroid carries a memory that stretches far beyond the birth of the planets. Their surfaces hold scars from primordial collisions. Their interiors lock away minerals that once drifted freely inside the young, glowing nebula. Their paths travel like threads that connect the present to the first breath of creation. Scientists often describe these wandering bodies as drifting archives. They're silent yet expressive. They hold no voice, yet they speak through their structure and motion. Each orbit writes a silent letter that describes an event from the ancient age when dust and fire shaped the space we now call home. These letters remain scattered across millions of kilometers, waiting for us to read them with patience and devotion. As our instruments grew sharper and our journeys deeper, we uncovered new secrets. Some asteroids hold water locked within their minerals. This water is older than Earth itself. It formed before the oceans. It existed before any mountain or river. It holds a signature that predates life. When researchers analyze such ancient water, they gain insight into the chemistry of the early nebula. They discover the ingredients that gave rise to worlds. Other asteroids contain grains that formed around newborn stars that lived before our sun. These grains traveled through interstellar space before being captured by the cloud that later collapsed to form our solar realm. This makes such grains older than the system they now inhabit. They're visitors from forgotten stars. They're silent travelers that carry stories of cosmic fires that burned long before our sky existed. The deeper we explore these fragments, the clearer the portrait of our origin becomes. Their density, their magnetism, their minerals, their orbits, and their temperatures merge into a single narrative. A narrative that tells us the solar system did not appear in a single moment. It grew through countless stages. First came dust, then came clumps, then came the dance of gravity that shaped large worlds. Asteroids preserve the early stages while planets erase them through pressure and heat. For this reason, every asteroid that we visit holds unmatched value. It is a preserved page from the earliest chapters of our cosmic story. Without these pages, the origin of Earth, the Moon, and the other planets would remain blurred. With them, the tale becomes clear. We understand the forces that shaped our world. We understand why worlds carry different compositions. We understand how life found a suitable environment to rise. Modern missions continue to uncover new wonders. Recent spacecraft have captured samples that reveal organic molecules older than Earth. These molecules float through the solar realm as potential seeds of life. They survived radiation. They survived billions of years of cold. They survived collisions. Now in the hands of science, they reveal ingredients that may have contributed to the rise of biology on Earth. Thus, asteroids do not merely tell us how the solar system was born. They also hint at how life may have begun. They connect physical formation with biological possibility. They form a bridge between cosmic dust and living cells. They extend the story from the creation of matter to the emergence of existence.